This leg right here has an impedance of R plus SL, and that has 1 over SC, so I could say Zn, if I wanted to, was equal to 1 over R plus SL plus SC. Right? That's 1 over the first impedance plus 1 over the second. Y'all with me? Now from that point on, you know when S is 0, just look at this, when S is 0, I have 1 over R over 1 over R. So at low frequencies it's R, right? As you go to, you can figure out the resonant frequency, that's when S, really resonant frequency is what? S is equal to J omega, and omega self-resonance is just 1 over square root of LC. Correct, class? Are you with me? Now we can go through and manipulate this to death, but if you've got the value for R, just from that plot, you can get the value for C and then L. Now, what question did you have now that I said that?
Nothing. You covered it in the beginning.
But this is the, go ahead, Nick.
So if you know R, how do you solve for LNC?
Well, if I know R is 4,700, I can look at a graph where this thing happens, right? It's a Bode. Now I know this frequency, and I set it equal to 1 over 2 pi RC, and I can solve for C. Once I have C, I can look at the self-resonant frequency, and I can solve for L. That's it. We could do the same for a capacitor, we could do the same for an inductor, but fundamentally, the curves are what you need to know. Okay? That's it. Okay. Yeah.
This last thing. So, like this process as far as, like, that first equation being right there, will that always be like the same process for any graph we would see?
You mean that one? Which equation are you talking about?
Like 1 over 2 pi.
Now this is for a resistor, right?
Just resist. Okay,
What
so
happens with a capacitor? Capacitor comes in from infinity, hits self-resonance, then it goes up, correct?
Mhm.
Now that's a capacitor. That's an R, L, and C. And you get R at resonant frequency. You can see the low point is where R, the value of R, right? If it's an inductor, it does what? This, right? The very low frequency is the value of the resistor you can extrapolate from, right? And then you get the self-resonance. Now, they usually give you the value if it's an inductor of the inductor, you know, because that's not the parasitic component. And you can calculate C from the other part. Okay? Did you have something?
No, it was that I was a little confused about, because you'd gone over inductor and then I'd understood the resistor on the homework.
But here's
gone
the-
over capacitor and then done the resistor on homework and then the inductor, but you just explained it.
I tell you what I do if I ever wonder about things in books. I take a functional form that they're estimating with a Bode, and I put it on MATLAB, or I put it on Octave, or MathCAD, or Mathematica, and I just put the log of the impedance on this axis versus the frequency, and you'll see it's pretty evident what element it is and where the frequencies occur. Okay? That's all I do. I take log on this axis, log on that. So if you want to, you can put just, in MATLAB, it's the plot, it's log of Z, and it'll put log on the horizontal, log on the vertical. Now it's log, log, remember that. It's not log10 when you do a plot. Go ahead.
Would you mind like plugging the numbers and see how it works? How can
Well, if I have 4,700, right, I would say 4,700 would be equal to 1 over 2 pi RC, right? Or sorry. I'm doing this completely. Hold on. What I should do is say this I'd have this resonant frequency would be F low. So I'd say F low would be equal to 1 over 2 pi, right? R times C. Well, I have R as 4,700, so I get C as what? C would be 1 over 2 pi, right? Then it's 4,700, correct? Then it's whatever F low is.
4,700. I can do
But
that.
I mean, this is just just changing and solving for the unknown in the equation. There's nothing difficult. All right. Any other questions before I move? Because there's Well, you can go through every permutation in your mind. But that's it. And you can work from this equation and get that if you want. You have to make the assumption that R is going to be significant compared to the impedance of C and L. When you talk with the impedance of L, you talk about low frequencies, but that's it. All right. Now, next thing I'm going to talk about is digital signals. I want to say something that Dr. Whitmore's book treats this thing extremely briefly. And I want to say one other thing. This is important, really important. Now, the reason I'm saying this is with FCC law, everything you do when you engineer things on a microprocessor, it's digital signals. Apologize, man. With digital signals, the thing is, everything has a rise time and a fall time. It's 5 volt, it's 0 to 5 typically for digital systems. I'm not even sure anymore. It used to be 0 to 5 volt changes for a typical digital clock signal that would feed things on a breadboard. Nowadays, I'm not sure. Are they down to around 2 volts now or less? Really what they worry about is the speed. And the rise time, fall time dictate speeds, particularly rise time. I'm going to go through this with you, and I'm going to show you how, when we take a look at digital circuitry, how we do the analysis in the frequency domain. This is important. Dr. Whitmore's book only glosses. I'm going to go into detail of this. All right, so be attentive. I'll call it digital waveforms. So in general, if you talk about a digital waveform, what it does is this. It's going to have something where it starts, it'll have a rise time, then it'll have a hold time, then it will fall, and it'll repeat itself as such. This is versus time. And you can say this signal is just going to be x of t. It's a voltage. It's got some height A. Now, I'm just trying to show you a square pulse that's repeating itself with a rise and fall time. And I'm doing the way it's normally done. They estimate the rise time as some short duration, where this is tau rise. Typically, the rise time is the thing that dictates, so they let the fall time be the rise time. That's not always true, but generally speaking, the rise time is the critical feature. That's the reason we assume it's the same. Now, there's something called the on time, or tau. And that's about from the 50% point, where it's 50% up, 50% down. And the symbol is tau. And that just means the amount of time that it's on over the actual portion of the waveform that's repetitive. Next, you're going to have the period t, sometimes called a pulse repetition interval. And that's the time over which it repeats itself. All these things are standard terminologies that you've seen. You've seen rise time, fall time, you've seen duration. Something else called the duty cycle, right? It's usually EC or duty cycle, and that's just tau over t. It's the percentage of the waveform time that it's on. Do y'all remember this?
We just had to do a lab on this.
Okay, so this is nothing new to you, right? All right, this is all just common. And what a typical duty cycle is about 50% normally, right, for most clocks. All right, and in radar, when they talk about duty cycles related to a transmitted pulse, you get down to 10%, 0.1 or less, because you want a short duration pulse in order to get resolution, distance resolution. But that's something well beyond this. So when you take a look at this, first it's periodic, right? Anything that's periodic allows you to do what? I'll put it over here. You can expand it in terms of a Fourier transform, right? Fourier series. It would be some C of n e to the j n omega naught t, where n would go from minus infinity to infinity typically, right? And you all remember that kind of stuff. And then you find out that what? C of n was equal to 1 over the period, the integral over a period, it can be from minus t t over 2 to t over 2 of x of t e to the j minus j n omega naught t dt. And you find out that omega naught itself is what? 2 pi over the period t. And those are just the standard things you learn when you get signals and systems. All engineers are going to be using this stuff forever. I mean, unless you're in sales, generally speaking, this stuff crops its head up all the time. So you get used to Fourier series, Laplace transform, all that stuff, solving equations with Laplace transform. Y'all with me on that? Now keep an eye over here. Something else that happens, it's important. And you know this, and you know this, and I'm not sure about who I taught signals and systems, but if you had me for signals and systems, you got this. If I take a derivative with respect to t, dx dt, then I end up getting, I look at this quantity, and now I get a summation of jn omega naught times c of n e to the jn omega naught t, from n goes from minus infinity to infinity, don't I? I just took a derivative of this series with respect to t, so it brings out the jn omega naught c of n as a constant for any given wave. This is bringing back memories, I know. I'm sure with you, and anybody else besides these two having for signals and systems? No. Well, you're about to learn something that's valuable. If you, I don't know if you were taught it if you haven't had it. Now, this is important. This term, and I'll box it, is actually a constant, and it makes the second series of the derivative series look just like the first series with a different constant. This right here is a constant. You can call that c prime of n. And that's equal to jn omega naught c of n. So if we had this value, that's a Fourier series, and cn of prime would just be 1 over t times the integral from minus t over 2 to t over 2 of the actual function, in this case, dx dt times e to the jn omega naught t dt. In other words, this function right here replaces the x of t, and now we can calculate the Fourier series coefficients for this series. You all with me on this? And we can keep going down. That's one derivative. If I took two derivatives, it would be j and omega naught squared times c then, right? If I took a double derivative of x with respect to t, then this term right here would be squared. It would come out twice. You all agree with that? Now, this is important. So when we look here at this wave, I'm going to erase that and draw a little higher so you can see it. And you use digital circuitry all the time, but a lot of times people don't know what the spectral analysis should look like. Here I'm going to abbreviate this signal, make it smaller. So if it looks like this, and remember, this is tau, this is the rise time, this is the fall time, which is going to be the rise time. All right? When I look at this, and this is t, now, please be attentive here. This is x of t, right? I'll give you something to look at when I'm done. Now what I'm going to do versus t, I'm going to go ahead and take a derivative of x of t with respect to t. What does a derivative always do? It takes the slope of the line, right? Right? So if I look at this, I can see it goes, well, this has a rise of a over a time of tau, doesn't it, class? I mean, excuse me, tau rise. So this point would be a over tau rise here. It would be a constant, then it hits this point, right, which is tau rise, and it's 0. It comes over, and then here it goes negative. I hope you all see this, right? And this is got a width of tau rise 2. You all follow me in this class? right? Now that's a periodic series. It'll keep doing that over here, right? Are you with me, everyone? Now, what happens if I take another derivative of this? What happens?
You just have the 0, right?
No, what happens? There's one thing happens. It goes from 0 to a height instantly. What do we call that?
Oh.
Delta function, right? It's an impulse or delta function, Dirac delta. So now we say we have an impulse here. Now this is going to be the second derivative of x with respect to t squared. Now we get a double derivative, we get an impulse. And the way they normally show delta function, they'll just put an arrow there. It's assumed the delta function exists. And the weight on the delta is a over tau rise. Keep going on this one. What happens when I hit here?
Down.
2 minus.
Minus.
Right, yeah. And so here it will go to minus a over tau rise. And then here, minus, this is a mess, this is going to be minus a over tau rise. And then finally right here, it goes up to a over tau rise. And then it repeats itself. You all follow me? Now those are impulse functions, aren't they? You know why I like impulse functions? Getting C of n is trivial. That's the reason I like it. So now with this one, what I really got is double derivative, so I'm going to do something here to make it a little more apparent. I'm just going to take this and make it the second derivative. Here would be squared, right? Right, that's still, and then Cn double prime would be Jn omega naught squared there, and this would be the second derivative here. What I'm trying to do is just adapt what I had on the board to the second derivative point, all right? Now just listen to me. If I get this coefficient, this would be a double derivative right here for C of n, double prime, I can get C of n by just dividing by Jn omega naught. Do you all see that? You with me on this? So let's do it. First, let's get a Fourier series for this. So I know this function, I'm just going to call that double derivative, y of t. I can say that y of t is equal, since it is periodic, I can do this from n equals minus infinity to infinity of C of n double prime e to the Jn omega naught t. And now I can say C of n double prime is 1 over t. The integral, and you can go from minus t over 2 to t over 2 of the function, which is going to be y of t, times e to the j n omega naught t dt. Now, I didn't put in the actual delta function series here. I'm going to in 1 second. You all with me? Well, when I do the delta function series, I have 1 over the period t, and I'm going to have, and there'll be a constant of a over tau rise that comes out front. Then I have an integral from minus t over 2 to t over 2. And here I have a delta function that starts at 0, so it's just delta of t. And then I have minus delta of t minus tau rise, right? And then minus delta of t minus, and you can, since this was centered there, you can actually shift it. It's just t minus tau, right? And then it's plus delta of t minus the quantity tau plus tau rise. And this whole thing, let me erase this stuff, is going to be times, right, e to the minus j and omega naught t dt. In other words, now I'm getting the coefficients for this series, for this impulse series. Y'all remember doing this kind of stuff? This is so important. I'm doing it only with the exponential series. He shows you in there a sine, cosine series, a trigonometric series. Forget those. They're never really used for anything other than, I guess, mathematical discussions. They really don't benefit. Now, if you take a look, what is a delta function? What's the one thing a delta function does? When I'm integrating anything times a delta function, I find out where the delta function turns on, and I evaluate whatever constant is next, or whatever function is next to it, right? Is multiplying. So this means that this entire thing would be equal to A over T tau rise right here. That comes out in front. Then delta function turns on at 0, first one. Evaluate e to the j0 is 1. Right? Now, when does this one turn on, guys? Can you all see that? Sure, t at the rise time. T. So now I evaluate t equals tau rise here. So I get minus e to the minus j and omega naught, and now that's tau rise. With me? Keep going. Where does this one turn on? Tau, right? Just tau. So now it's going to be another minus e to the minus j n omega naught tau. Finally, where does this one turn on?
Tau plus tau r.
That's tau plus tau rise, right? So it's going to be e to the minus j n omega naught quantity tau times e to the minus j n omega naught tau rise. I separated the two. And I have this as Cn double prime. Y'all follow me on this? I don't know if anybody knows what I'm up to next, but I bet you some of you can smell it. Anybody want to take a guess?
Are you going to put it all in terms of one period of time?
Well, this has nothing to do with time, does it?
Well, I mean like the taus. No, you're not doing that?
I'm going to turn it into sinc functions. I'm going to turn it into sines or cosines, right? Because I know sine is something I can visualize. So take a look at this just for a second. All right. I have 1 minus tau rise here, right? What happens if I have 1 minus tau rise times 1 minus tau? What do you get? Just think about it. In other words, I'm showing you what I'm going to factor to. If you have 1 minus e to the a times 1 minus e to the b, you get 1, right? Minus what? EA, right? Minus EB minus EAB, don't you? With me? Or plus, pardon, plus. Now look what you got. If I have, instead of 1 minus A, I have 1 minus Jn omega naught. And this is minus Jn omega naught tau. This is tau rise here. In other words, I replaced 1 minus tau rise is this part, and this part is going to be 1 minus tau. You follow me? I'm going to do right here. You go ahead and if you put these two together and multiply them, you're going to get that right there. Which means, that's my point of this, which means I can say that my C of n double prime is A over capital T tau rise. And then it's going to be 1 minus E to the minus J n omega naught tau rise. 1 minus E to the minus J n omega naught tau. You multiply them out, you'll get that up, get what we have right there, I promise you. Now what am I going to do? There's one thing I'm hoping you guys catch on to. I'm going to do this. What happens if I have 1 minus e to the, say, minus j n omega naught tau? Isn't that equal to e to the j, and this is going to be minus j n omega naught tau over 2 times e to the j n omega naught tau over 2 minus e to the minus Jn omega naught tau over 2. Isn't that right? Take a good look at what I'm about to show you. Every time you see this, think about this from now on. Whenever you see that 1 minus e to the j business, always think I can turn it into a trig function. 1 minus e to the j or 1 plus e. All right, now what is this functional form right here, anybody?
2 cosine.
What happens if I have sine of theta? That's e to the j theta minus e to the minus j theta over 2j. That's Euler's identity, right? No Euler's, believe me, you're going to use it all the time. So I multiply this by 2j, I get 2j times the sine theta. So this is 2j times this. And then times the sine of n omega naught tau over 2. Agreed? What do you think I'm going to do to the next term? That was with what? That's tau. For tau rise, I do the same thing. Do y'all follow me? For tau rise, I'm going to get 2j e to the minus j n omega naught tau rise over 2 times the sine of n omega naught tau rise over 2. Do y'all follow me? And that's going to be C of n. Now, well, if you don't mind, I'm going to erase this and put it up top here. This is one of the things I've always liked about physics. They usually have 3 boards that they can slide up and down easily. And I love those. I wish I had. I've never had that in engineering. I think engineers use overhead paper and PowerPoints, but I never liked it. So now I'm going to say that my C of n double prime was equal to, down here, A over tau, right? Tau rise times T, right? And then it's going to be times 2j squared times the sine of omega naught n tau rise over 2 times the sine of omega naught n tau over 2. And that's C of n double prime. Agreed? All right. How do I get C of n? I divide by j n omega naught. Don't I, class? Y'all see that? So if I divide this by j n omega naught, but it's squared, isn't it? Because I took in 2 derivatives. Now I have the C of n coefficient for the original Fourier series. Do you all see this? This is so important. With me on that? Now take a look at this for a second. See what you can make of it. You see how I have a j squared there and a j squared up top? Everybody? I'm going to get rid of the j's for starters. Now what else happens here? Well, you remember what a sinc function is. What is the definition of sinc of x? That's the sine of x over x, isn't it? Now that's the standard definition that we use in the signal processing book we're teaching from Ulaby. But there's another definition where there's actually sine of pi x over pi x that's used as well. We're going to use this one here, okay? So if I do this, take a look. For the first term here, I need omega naught n tau in the denominator. Do you all see? Let me expand this a little. All right. Well, I'm working on this one. So I don't have a tau downstairs. So what I'm going to do is put a tau here, right? And then I'm going to put a tau here. Are you with me? I'm multiplying top and bottom by tau. I'm adapting this. What I want is the actual omega naught n tau over 2 downstairs. Now there's a 2 squared, so if I divide this by 2 here, then I have sine of x over x, where x is n omega naught tau, right, over 2. Do y'all see this, class? You see it, man? And Nathan, all right, so that's a sinc function. I'm taking it in that sinc function. I got another 2 here. I divide that by that. Top and bottom by 2, right? And I got a tau rise here. And now I find out that my value for C of n is A times tau over T. That's the duty cycle, times the sine of n omega naught tau over 2 times the, or not sine, sinc, pardon. I'll call it sinc function. NC of that times the sinc this is tau rise over 2. Are you with me, everyone? Tell you what, I want to finish this up. Can we do the quiz Monday? If you really want it today, I'll give it to you today. You want it today or Monday?
Today.
Monday?
No.
How many want it on Monday? 1, 2, 2. Was there a third? How many want it today? All right, we'll do it today. I'll give it to you in 1 second. I wanted to just finish this, but we'll do it today. If you take a look at this, right? Here's the thing. This sinc function and this sinc function fall off as 1 over n omega naught tau over 2. I'm going to give you some rating on this. And the beautiful thing is, you can tell the thing that really is going to drive the rise time, or drive the bandwidth when I plot this, and it's this term right here. Because this term will have a much wider bandwidth. And we'll talk about the null on that and the actual bandwidth on Monday. I'll give you a quiz now. I didn't get through there, but this is sort of the real way to do analysis in the frequency domain of any kind of signals that have rise time, fall time, and on time. Yeah.
You had a tau rise in the denominator, the A tau over T.
Yeah, I needed it over here when I have the sine of n omega naught tau rise over 2. I have to have n omega naught tau rise over 2 downstairs. You get the sinc function? Right, so I took the tau rise and I put it over here. So I have this and this are the same. See? That has to be the same as that to replace it by a sinc. And that's what I did. I'm going to give you some reading material on this and ask you some things, but it's really nice to do this and see it for yourself. It's very useful. Okay. Quiz. You want to